Welcome to our module on the eye. We'll start by introducing this particular video introduces some information about the eye, and we'll do a little bit more in the next segment, and then we'll kind of get into electrooculography, which is all part of this module. So again, recognizing that the human body works a little differently from the machines that we've created to mimic it, the eye and a camera focus differently. So the camera just changes the distance between the lens and the film in the old-fashioned way of talking about it, whereas the eye changes the shape of the lens itself. So the cornea and the lens bend the light rays coming into the eye and then focus them so that they can be projected onto the retina. And again, the focus is accomplished by changing the shape, such that the thicker the lens is, the more nearby the focusing is, and then it thins out to focus on a distance. And this is accomplished with the ciliary muscle, stretching and bending and changing the shape of the lens. So the eye has on the retina the light-sensitive photoreceptors. And you probably know these from other classes where you've studied. The rods are for that dim light, and they're also optimized for seeing movement. And then the cones are for daytime vision, focusing more on precise details, seeing the actual visual details of things. It's for color vision, and they're clustered around the fovea. And we'll talk a little bit more about the fovea. So here's a schematic diagram of the eye. There's the lens, which changes shape to focus things from farther away or closer onto the back of the retina here. The fovea is right here. This is where the actual density of the cones is at its highest. So for very specific, precise vision, seeing the details of an image, you're going to foveate. You're going to aim your eye on whatever you're looking at such that it hits the fovea square on. And then down below is the optic nerve, where all the information from it's gleaned from the retina is passed back into the brain, back to the very back, the occipital lobe. So this is a helpful graph that shows the density of the rods and cones at different points from the fovea. So at 0 degrees, that you're right on the fovea of the eye itself, and you'll see this incredibly huge density of the cones. So these are giving you the best precise color vision that you can get when you're identifying an item that you're putting on your fovea that you're looking at. Now, as you get farther out from the fovea, the density of rods picks up. And then so that's allowing you to see better movement and to see well at night. So if you think about if you're ever walking around on a not so moonlit night and you're trying and something's rustling in the bushes and you really badly want to see what it is, your instinct is to foveate, put it directly on the fovea. But cones are no good in the dark. And so you're often probably having this futile, frustrating effort to try to see what it is and not being able to see it all because you're staring straight at it. So if any of you have noticed this technique, if you're trying to see more precisely something that's rustling around in the dark, you actually look slightly off-center from the item that you're trying to look at and kind of pay attention to it with the rest of your brain, and you'll be placing it at the peak of where the rods are. These are best optimized for night vision, so you're going to see much more detail at that point, looking slightly off-center from the object and try to putting it on your mind's focus and picking up as many rods as you can to focus on it. This is the blind spot here, and if you were in a live class, I would see if anybody knew what the blind spot corresponds to. But since we're not in a live class, I'm going to go back and show you what corresponds to where the optic nerve is. So there's no retinal cells there to receive any information, so you literally have a blind spot there. And that indicates where it is in your degrees off of center, off of the fovea. So there you're visually fixating on the fovea. You're centering the image there. Okay, there's different aspects of visual fixation. Voluntary fixation is where you're foveating, where you're staring right at the thing you want to see and you're locking into it consciously. You're making a conscious effort to see it. Involuntary fixation is this unconscious process that allows you to remain locked into it. So once you've foveated, once you've identified what you're wanting to put on in your vision, involuntary fixation helps you stay focused on it. It helps you remain locked into it. So what this is, just to kind of explain it in a little more detail, after you've locked into an object, the eye is actually continuing to move. You don't know this, you're not making it move. You're actually, in your mind, you're staring straight at something and you're staring consistently right at what you're doing. But the eye is making these tiny, repetitive, imperceptible, jerky, minute movements. And they are serving to counteract, they're called microsaccades. They're serving to counteract this perceptual fading that happens. Vision works on an opponent process system where it needs contrast, it needs continual contrast. So if you're staring at the same thing for very, very long, if you don't move your eye, it will just fade from view because the eye adapts to what it's seeing and says, this is nothing new and this is nothing I need to pay attention to. So the microsaccades actually keep your eye moving around so that you can continue to stay focused on that image and it can continue to stay fresh in your visual perceptive field. So these microsaccades sharpen your visual acuity. Saccades are a little different. They're not micro, they're a little bit bigger, but they have that similarly rapid ballistic movement of the eye. And these are the movements that you'll make when you're reading a passage. Your eye is moving from chunk to chunk as it moves along the page. And it involves changing your point of fixation. So this is actually when you're consciously needing to get from one place to the next along the page. You need to see different parts of the words. So it can be small in this example while you're reading, or it can be larger when you're scanning a whole room and your eye is moving around. And I have just a little image, and it looks kind of weird if you look at it too long, but this is somebody's making saccades with their eye. So saccades can be voluntary or involuntary. A little bit more about saccades. This visual fixation can tell us something psychologically about where somebody's looking. So if you use something like electrooculography to measure where the eye is, you can get a sense. These are eye tracking software that was done of somebody looking at this image. And different people with different psychological conditions can have different patterns here. This is a person, this is, I think, quite typical of someone without any particular disorders or issues. They tend to spend a long time looking at the eyes, a little bit looking at the mouth, nose area, and kind of triangulating between. There was a lot of looking at kind of this part of the hair here. So scanning for what's important visually to a person. Typically, the research on autism shows that most people are a little bit more avoidant of the eye area. You would be likely to see a slightly different pattern. So this is the way in which electrooculography and measuring eye movements can help us understand something about their psychology. So I'm going to take a few minutes to go into the eye muscles. This was covered in the introductory PDF file, so I want to kind of break it down a little bit. It was covered a little bit cryptically with a bunch of initials, and you're supposed to know what they all are. But there were 6 total muscles. I'm breaking it down into this batch of 4 and then the other 2. These 4 are the rectus muscles, and rectus means straight. So this is where the muscles are coming straight from the insertion to the origin. So they're kind of at these 90-degree angles from each other, forming the plus. So, and then just knowing your how things work with superior, you're in anatomical issues here. The superior rectus is superior. The inferior rectus is below. You should know these anatomical terms. Lateral, and opposite of lateral is medial. So if you were to know these are the four: superior rectus, I think they just abbreviated these SR, lateral rectus, LR, etc. But if you kind of know your anatomical terms, you'll know where things are. And if you knew these terms, you would know whether we were looking at somebody's left or right eye. You would start by this medial indicator here, and from there you could guess where the nose is. If the nose is here, if the nose is here, the nose is medial. And then from there, you would know that you were looking at somebody's left eye, to the left of the nose. So there's the nose. Now, the other two of the 6 muscles that were introduced in the introductory piece was the oblique muscles. So they are attached obliquely to the eye, kind of at more of this angle. They're not attached in this straight rectus way. So, and the 2 oblique muscles that were introduced were superior and inferior, but they control the eye muscle a little bit differently from the rectus muscles. So the superior moves the eye down and laterally, and the inferior moves the eye up and laterally. So it kind of moves them at an angle more, not at these straight plus and minus degrees. So altogether, those are the muscles and the control of the eye. There they are, so superior rectus, superior oblique. Now you can make sense of what those initials were. And so the movement of the eyeball is created through the movement of these 6 muscles. And they're controlled by cranial nerves 3, 4, and 6. So EOG, electrooculography, other ways that it's used in psychology other than some I introduced, they're very useful for infant studies because infants are pre-verbal. They can't tell you what's on their mind. People typically use eye tracking technology. What they've found with infants is infants tend to track, they're attracted to novelty. And so seeing where their eye is going is going to tell you something that they find interesting, and maybe some learning as well as being revealed through where their eye is moving. Eye gaze is also used for social measures. A lot of times there's a mother-infant dyad that's being studied, and they'll look at the infant's eye gaze to see whether they're attached to their mother or attending to their mother, or whether they're looking away from their mother. It's also very useful in nonverbal populations, even beyond infants. We have a colleague here in the department who is studying minimally verbal people with autism, and she uses different techniques to try to get at what's going on in their psyche without the benefit of the verbal discourse that you can have with other populations.